Thank you so much for having me here. As I was saying, before I begin, the work that I am going to present is the result of national and international collaborations with colleagues from academic institutions, charitable organizations and industrial partners who are acknowledged along the way. Also, I would like to dedicate this lecture to my rescue dog, Zina, who worked with me on some of our ACI projects and who passed away 2 days ago. There will be video clips of her in the presentation, so apologies in advance if my voice alters slightly when we come to those. Now, for millennia, much of the technology we have developed has advanced human interests by making it increasingly easier for us to outcompete or exploit other living beings and their ecosystems. With the advent of computing and with developments such as the Internet of Things and artificial intelligence, animals in particular are being increasingly impacted by technologies whose design is still all too often fundamentally human-centered. In contrast, the growing field of animal-computer interaction, ACI for short, focuses on the nexus between animals and computing technology from an animal-centered perspective. In particular, the Open University's Animal-Computer Interaction Research Program was set up in 2011 on a mission to advance the art and science of designing animal-centered interactive systems for a multi-species society. Its aims are studying different kinds of interaction between animals and technology within their habitual contexts, designing computing technology that improves animals' welfare, supports animals in their activities, and fosters intra and interspecies relationships. And importantly, developing animal-centered approaches to design technology for and with animals as legitimate stakeholders and design contributors. With the following examples, just a few examples of our work, I will try to illustrate how we pursue these aims across species and contexts. Now, firstly, it is important to understand how even the best intentioned uses of technology may impact animals and how to minimize these impacts. For example, this project investigated how to minimize the impact of wearable animal trackers by improving what we call wearability. Animals are often fitted with devices that track their movements, behaviors, and vital signs for conservation, research, and husbandry purposes. However, animal wearers, the primary stakeholders, have no control over their use. Devices can interfere with their body, for example, injuring or trapping them, and activities, for example, slowing them down or disrupting their camouflage, thus impacting their welfare and also the quality of recorded data. And existing guidelines for designing these devices still tend to be rather coarse and ad hoc. So we adapted values and principles informing the design of human wearables to develop a framework that could support a wearer-centered approach to the design of animal wearables. The framework is underpinned by the fundamental values of non-deleteriousness and minimization of effects, and by 3 design principles stating that the presence of tracking devices on the animal's body should ideally be imperceptible, or at least unobtrusive, or at the very least cognitively acceptable to them. All stakeholders should be considered, primarily the wearer, but also their significant others, that is, their social relations, such as mates and offspring, and asocial relations, such as predators and prey, and of course human users too. Whereas biological characteristics, their activities, and their environment should all be considered, and all possible design variables, along with technical variables, should be exploited to maximize wearability. The example on the right suggests that when designing a tracker for red foxes, the device should not emit background noise that is within the hearing range of the fox, but also of her potential prey and predators. And this is just one small aspect that will need to be considered. Now, as a case study, Patricia's behavior observation of cats wearing different commercial GPS trackers showed poor wearability, even though these were marketed as cat-friendly. In contrast, her behavior observation of the same cats wearing a tracker that she had redesigned using the same electronic components but applying the framework showed significantly better wearability. Now, collecting animal data in non-intrusive ways is particularly important when animals are asked to perform tasks that require concentration and precision, as is the case for biodetection dogs. Biodetection dogs are trained to recognize and indicate the presence of organic volatile compounds from disease cells in biological samples, such as urine or sweat, but the signaling conventions they are trained to use for human convenience, such as sitting down in front of a positive sample, do not enable them to communicate all that they know because these conventions are binary signals that do not express nuances such as a compound's concentration levels, and because they impose a translation overhead on the dogs that lowers the signal's reliability. With medical detection dogs, the charity that pioneered biodetection with dogs, we wanted to find a way of accessing the dog's knowledge about the samples they sniff without them having to translate for us. We wanted to center the practice of biodetection on the dogs themselves by shifting the translation burden onto the technology, hypothesizing that the dog's spontaneous response to the olfactory stimulus might be proportional to the stimulus presence and intensity. We designed a device that used pressure sensors to record the dog's interaction with the samples and capture their stimulus response. Early tests with solutions of amyl acetate, that is, banana essence, showed some consistency in stimulus response between different dogs, with an interaction pattern emerging when the dogs encountered positive samples. And it seemed that there might be proportional variation in stimulus response depending on sample concentration. This suggests that the data may lend itself to machine learning approaches and the preliminary application of convolutional neural networks to classify the dog's responses has already yielded promising results. Now, medical detection dogs are currently using the latest version of the technology, which you see in the video, in their colorectal cancer detection project. The new apparatus captures both pressure and proximity data, which we are looking forward to analyzing, as we have a PhD student starting on this just this October. Now, while the aim of the previous project is to allow dogs to focus on their work without taking any notice of the technology, in some cases, dogs have to engage with technology to negotiate their way around their living and working environment. As a case in point, mobility assistance dogs trained to interact with various technologies on humans' behalf have to operate in human-centered environments that, from a dog's perspective, contravene the most fundamental interaction design principles. This results in poor canine usability and user experience, impacting not only on the dog's training times and performance, but also on their welfare. So with Dogs for Good, a leading charity in the sector, we wanted to rethink the way in which ambient interfaces are designed to make them more user-friendly for dogs. We wanted to develop a portable kit of controls that could be retrofitted in the dog's living and working environment to make it easier for them to operate within it. We applied established design principles and usability goals according to the dog's specific circumstances, including dogs' sensory abilities, for example, their diachromatic vision, their cognitive abilities, for example, the way they categorize objects, their physical abilities, for example, their snout's dexterity versus their limbs' strength, their activities, for example, opening doors, switching lights, calling elevators, and the environment in which these activities take place, that is, their domestic and urban settings. Our research shows that input devices designed according to these criteria make dogs' tasks much easier. For example, Louisa's comparison of our early controls against standard issue access controls for opening a motorized door showed improved usability based on parameters such as overall time to open the door, number of contact attempts made, and attempts necessary to activate the control. Here is a short video of my dogs using the same controls after only a couple of short training sessions. They were not specially trained dogs, just rescue dogs who lived with me, and just to show how with a very light touch of the nose they can open a very heavy door, and which they learn to do very quickly. Luisa further developed the design of our next generation of wireless cylindrical controls, testing different sizes as well as push pads with concave and convex profiles. She found that a control with a diameter of 120 millimeters and convex push pad performs best for dogs of different sizes. In particular, although the concave pads guided the dogs now towards the center of the control, inviting a more precise interaction, the convex pads enabled the dogs to activate the control from any angle. This provided more flexibility regarding their placement in the physical environment, which is critical for usability in small spaces, and which illustrates how the devil is in the details when you design for animals. Now, following further improvements, our final wireless prototype, which is just about to come to market, allows dogs to easily control aspects of their environment, such as activating a range of domestic appliances. But beyond facilitating animals' functional interaction with their environment, sometimes the design challenge is to provide them with enriching user experiences. In particular, this project aimed to provide acoustic enrichment for elephants living in zoos. Overall user experience depends on the controls used to provide input into a system, for example, a button, on the output provided by the system in response, for example, a sound, and on the wider context in which the interaction occurs, for example, environmental noises that may interfere with sound output. As Fiona found, designing acoustic enrichment for elephants highlighted how the interaction needed to be intrinsically rewarding regardless of the outcome. The elephants showed great attention towards the sensory experience provided by different input devices, which were objects of interest in themselves. This highlighted the importance of considering the animal's aesthetics experience to design appealing interactions. Here are examples of prototypes that Fiona designed to enable elephants to control sound output, including wood and textile vibro buttons, knitted buttons, and copper radio buttons. And this is an elephant jukebox, which used copper radio buttons to trigger different pre-recorded sounds and which was installed in the indoor habitat of 2 elephants residing at Noah's Ark Zoo. Sometimes, though, enrichment interventions in isolation are not sufficient, and a more holistic approach to the design of animal habitats is needed to meet their welfare priorities, as this project aimed to do. Many wild animals live in settings which lack the complexity and stimulation of the environment in which they evolved. For example, in the wild, tigers have extensive home ranges and spend their time patrolling their territory, foraging, hunting, or mating, whereas in zoos, they have limited space and everything is provided for them on a schedule. So they have little opportunity to engage in activities that in the wild would involve meaningful movement. However, research conducted by Care for the Rare shows that meaningful movement is a major welfare priority for tigers. So this was the starting point for designing a whole interactive environment to provide rescued tigers with such opportunities. The sanctuary where the tigers we worked with reside has created a new complex of interconnected outdoor enclosures. 3 of these are connected via a large building where our interactive system is installed. The building hosts an interactive maze consisting of 3 concentric irregular rings and an elevated central island. The rings are connected by 2 diametrically opposed gate systems, which will open and close to reconfigure the space and provide multiple routes to and from 5 different locations: 3 outdoor enclosures, 1 indoor den, and the elevation of the central island. As the tigers travel through the maze, olfactory, acoustic, and visual signals associated with different locations will guide them around the perimeters and through the gates. At specific points, the gate's configuration will present the tigers with route options, giving them the opportunity to make choices to reach specific locations and the resources within them. Infrared sensors all around the ring's perimeters will allow the system to identify the target's location and trajectory and to dynamically adapt gate configurations and signals accordingly. Here are some photos of the site under construction showing the interactive gates, the infrared sensor posts, the lights, and the suspended gantry on which speakers, lights, and scent emitters are mounted. We have almost finished installing the technology and are looking forward to working with the tigers themselves to adapt the functionalities of the system to their individual usability and experience needs. But what if we could give animals tools to tell us what they need and want? How should we design these tools then? This project addresses these questions based on Jennifer's work with cockatoos over the past decades. Millions of parrots live in captive conditions in which their complex cognitive and welfare needs are not adequately met by environments that are unsuited to their evolutionary characteristics and that severely limit their agency. To help address these challenges, Jennifer has taught her cockatoos to use a speech board. This is a tablet-based application featuring menus and submenus of options such as pictures and drawings representing objects and ideas that might be relevant for the birds, including food, games, places, and even affective states like emotions. She has leveraged associative learning rules whereby each option becomes associated with a corresponding outcome to teach the birds the meaning of the different representations so they could use them to communicate with her in their daily life. We examined the interaction of one of the parrots, Ellie, with her speech board through the lens of Jacobson's communication model, which identifies 6 possible functions of communicative utterances. We found that Ellie's speech board selections map onto 4 of Jacobson's functions, mostly the cognitive function with requests for cognitive or environmental enrichment, for social interactions and for resources such as food and beverages. Then the emotive function with expressions of affective states such as contentment or discontent. Then the pathic function with selections akin to chit-chat. And lastly, the referential function with observations on aspects of her environment. Now, Ellie showed intentional and persistent functional communication. When menus were randomly rearranged, she found her favorite items regardless of their placement. She was persistent in requesting things when these were purposely denied to her, and consistently refused things that she was given instead of those she had asked for. When she received what she wanted, she corroborated her original selections by consuming the requested item or engaging with the requested activity. In this short video from a menu featuring different treats, Ellie selects sunflower seeds, but is instead offered first broccoli and then other seeds, both of which she refuses. When she's finally offered sunflower seeds, she consumes them. Then she closes the treat menu, opens her tablet's picture gallery, she searches for the sunflower seed thumbnail, magnifies it, and sits back, leaving it up there open for her caregiver to find. Now, as Ellie has become more proficient in the use of the speech board, her selections seem to have gradually shifted from making requests for enrichment and resources to expressions of inner states and space-temporal references. The table you see here shows the top 20 selections of options during different periods, including the number of times an option was selected, in the period, the number of submenus, and the tier of the submenu tree in which that selection could be found. So this work opens some interesting questions, especially if she uses the speechboard for self-expression. Could this kind of tool become a reliable mean for birds to self-report? What interface design, including items representational, arrangement, and categorization choices, would best support parrots' functional communication? What are parrots' sense-making mechanisms at play here? Is it just associative learning, for example, and the resulting conventions? Or do they recognize the iconic representations as representations of something? And if so, what is the level of fidelity of these icons they need to recognize them? To begin to answer these questions, we have looked at the parrot's spontaneous speech board selections prior to any training, dividing these into
నీ
iconic
ఫోన్ లేదా నీ ఫోన్ త్రూ ఈజీ ఉంటుంది.
Um, is it okay for me to continue? Oh, so dividing these into iconic photos, portraying familiar objects she might recognize. What we call pseudo-iconic photos, portraying unfamiliar objects she is thus not likely to recognize. Iconic drawings, representing in some detail classes of objects that she is familiar with. And pseudo-iconic drawings, representing stylized objects like the thumbs up, but they have conventional meaning for humans. And finally, abstract signs whose meaning is entirely arbitrary. We have also looked at how the spontaneously selected options are distributed across the speechboard screen to see whether their distribution might bias the part selections. This work is currently under review, so watch this space if you would like to learn what we found and what our findings suggest for further investigation into the design of speechboard interfaces for parrots. Now, consistent with what we have seen so far, a tenet of ACI is that whenever possible, designing for animals is best achieved by designing with them. And in this regard, the ethical and methodological perspective with which we approach the process is key. In other words, supporting animal-centered research and design requires an animal-centered ethical approach. So above and beyond existing regulations, which are largely inadequate from our perspective, our ethics framework is grounded in 4 key principles. Relevance, which requires working only with animals for whom the research is directly relevant and beneficial. Impartiality, which requires protecting all participants in virtue of their role rather than their characteristics, such as age, sex, species, or assumed levels of sentience. Welfare, which requires ensuring all participants' physical and psychological well-being at all times. And consent, which needs to be obtained from all participants, including animals. Importantly for us, animals' consent takes 2 complementary and equally necessary forms. Mediated consent, obtained from human guardians who know the animal well and understand the implications of their involvement, who have their best interests at heart and the legal authority to decide on their behalf, and contingent consent, provided by animal participants who must be allowed to continually assess the situation and choose what to do, whether and how to engage, while appropriate monitoring of any manifestations of dissent should enable guardians to respond accordingly. In a nutshell, doing animal-centered research and design implies respecting participants' autonomy and safeguarding their integrity by working in contexts that are habitual for the animal, by being unobtrusive and undisruptive of their habitual activities, by giving animals control and space for expression, and by using only positive forms of interaction. This approach is applied within an interaction design process that is quintessentially iterative and during which the design requirements are elicited using various methods, design concepts are produced, selected designs are prototyped, and then evaluated to identify further requirements. This is an open-ended process of incremental orientation towards a perfect final outcome that may never be achieved, but that can be gradually approximated over several iterative cycles. It is in this context that animals' ethical involvement becomes participation as it informs the design process. For example, in this project, we were aiming to design an alarm to enable medical alert dogs trained by medical detection dogs to call for help in a crisis. Although these dogs consistently alert their assisted humans to upcoming critical medical episodes, their humans are not always able to respond in time and may become incapacitated, which leaves the dogs powerless and in distress. The dogs needed to interact with the alarm as autonomous users, so the interaction needed to be safe, efficient, easy to learn, and to remember. This particular design concept comprised an electronic module that would trigger a call to a phone line and a biteable tag for the dog to use as an input device connected to the electronic module by a trigger. But what should the tag be like? What should its size, shape, texture, or material be? What kind of trigger should connect it to the electronic module? Should the tag detach when pulled or should it stay in place? How should the system give the dog feedback to let them know that they have successfully raised the alarm? To answer these questions, Charlotte used what we call quick and dirty prototyping to engage in physical conversation with our canine participants. She formulated a modular template for a canine alarm consisting of a tag for the dog to use as input device, a block of wood in lieu of the alarm's electronic module, and a trigger connecting the two. In this way, she could quickly present canine participants with successive combinations of different tags and different triggers. This dialogue suggested that the dogs preferred a simple and tidy setup not to confuse them, a detachable tag that worked as a form of feedback, letting them know that they had completed the task, and customizable tag and trigger resistance depending on the dog's age, training stage, and personality. And here is an example of a canine user in action with a customized tag. Now, for another example, we explored questions regarding animal participation by teaching my dog Zena to interact with the early versions of our dog-friendly controls, to open a small door and switch on a light. The coming short videos offer an example of how we take input and direction from our participants. Here we are already making progress with the training, which employs the luring method to help Zena associate her touching the control with the reward. I place a treat on top of it, so whenever she goes for the treat, she simultaneously triggers the control, which soon establishes a consistent association between the two events. At the same time, this creates a strong bias towards snout interaction, so interaction with the nose. Here, I'm trying to persuade Zena now to touch the larger yellow light switching control that is above the small door, which is a much more demanding task due to the control's height. She has done it a few times, but now she refuses sitting down and looking at me in a begging behavior instead. Here, she still refuses to engage with the light switching control. I could offer her a higher value reward to persuade her, but keeping the reward constant tells us that there is an effort threshold that we should not pass. Instead, I ask her to touch the lower yellow door opening control. Despite the bias towards snout interaction that I had previously created, she chooses to use her paw. So it is clear that she understands what the task entails, but elects to do it in her own way. She interprets the task and the action pattern required to complete it, and by rewarding it, I accept her interpretation. This has implications for design that will inform the next iteration cycle. For example, that the control needs to be located much lower, or better still, its height needs to be adjustable, that the pad needs to be sensitive to touch to respond to snout interaction, sensitive enough to respond to snout interaction, which can be very light, and robust enough to withstand paw interaction, which can be very heavy. That the pad surface needs to be comfortable for a dog's delicate nose to touch, whilst also withstanding claw abrasion, eventually leading to the final prototype you saw earlier. So far, we have looked at technologies broadly designed to support animals with a focus on their needs. But what about situations in which the stakes for animals are higher? Is it possible to design animal centered technology when designers operate within socioeconomic systems that are not animal centered? Addressing these questions requires dealing with the wider implications of animal centered design. This means being aware that design is an intrinsically political activity in which decisions are made that change the world and impact different constituencies. This inevitably raises issues of justice in general and of multi-species justice in particular, which we explored in this project. For this, we refer to Martha Nussbaum's political philosophy and to her capabilities approach, according to which animals are agents capable of dignified existence with corresponding needs for flourishing and related goals they actively pursue to achieve capabilities to which they are morally entitled. The approach does not demand interspecies equality or the abolition of all instrumental relations with animals, but it does require the fulfillment of animals' capabilities to at least an adequate threshold as relevant to their species. It also supports respectful practices that are compatible with animals' capabilities and that develop their excellencies and promote their flourishing. The capabilities approach to multi-species justice provides a measure of animal centeredness that could inform wider considerations when designing animal technology or when studies animals' interactions with technology. Here are some examples of questions that could help researchers assess the extent to which their work is animal-centered and thus conducive to multi-species justice. Additionally, among others, we propose 3 design strategies to promote animal-centered design. Disruption involves questioning systems, norms, and practices that go against animals' basic capabilities and that designers would like to address. For example, Natalia and I questioned whether smart dairy farms of the future might breach animals' entitlement to privacy and non-exploitation. Entitlements which can be successfully argued for by using already existing jurisprudence. Reconfiguration involves redefining design frameworks whose current human-centric definition legitimizes the dismissal of animals' role in the design process or justifies design outcomes that discriminate against them. For example, UC and I proposed a multi-species framework for participatory design to account for animal agencies and interests in design processes and outcomes. Pollination involves seeking opportunities to enable animal-centered values to influence systems and practices which involve animals but which are not animal-centered, to help such systems evolve towards animal justice. For example, Eleonora and I have been exploring the extensibility of ACI's animal-centered research ethics to all animal research. We have developed an ethical review framework that integrates the principles of relevance, impartiality, welfare, and consent for the iterative refinement of any research activities involving animals. But animal-centered technology is not just good for animals, it's also good for humans. Global governance bodies are increasingly recognizing that the interdependence of human, animal, and environmental well-being, and the inability of human-centric approaches to deliver sustainability. Arguably, an animal-centered perspective on the design, development, and deployment of computing technologies could support the pursuit of global sustainability agendas. For example, much animal-centered design is highly relevant to several of the United Nations Sustainable Development Goals. Consider the goal of good health and well-being. Animal-centered technology could foster beneficial human-animal relations, support animals who help humans, or improve animal welfare, reducing the risk of disease. Consider life below water and life on land. Animal-centered technology could engage people in conservation activities, enhance conservation efforts, and reduce human-wildlife conflicts. Or consider sustainable cities and communities. Animal-centered technology could foster beneficial human-nature connections within urban environments and facilitate social inclusion by involving marginalized groups in urban wildlife custodianship. Regarding these last sustainable development goals, I would like to end with a vision which brings together key points discussed so far and which resulted from a collaboration exploring the role of technologies such as artificial intelligence in the development of multi-species smart sustainable cities as a matter of justice. The United Nations have estimated that global urbanization will continue at least until 2050, which with cities becoming larger and more complex and facing increasing challenges with regards to their ability to sustain urban life. In response, smart sustainable cities are expected to integrate advanced information and communications technology within sustainable urban infrastructures. Digital sensing technologies, cloud computing infrastructures, middleware architectures, and wireless communication networks would be used to monitor and analyze urban phenomena and to plan and manage access to resources and services in order to meet the environmental, economic, social, and cultural needs of all their citizens. But urbanization is increasingly encroaching on animals' habitats, and animals are moving into cities, which have an increasing role to play in biodiversity conservation. Thus, in order to be sustainable, smart cities need to acknowledge animal dwellers and meet their needs too. In other words, we argue that smart, sustainable cities should enable animal dwellers to perceive, to make sense of, and to interact effectively with their urban surroundings as they pursue biologically relevant goals, including environmental goals such as building, inhabiting, and traversing structures, economic goals such as acquiring and managing resources, social goals such as forming and maintaining social groups, and cultural goals such as gaining and transmitting knowledge and skills. But how to determine what goals different species value and when these are adequately met? How to identify species to be considered and how to decide which species needs to prioritize? How to reconcile conflicting needs among species and compensate for lost opportunities? How to unambiguously communicate relevant possibilities to different species? And overall, how to enable different species to actively negotiate the urban environment. This is where smart technology could really help. Starting small, maybe with one species or a few in a location or two, and iteratively expanding to encompass entire urban ecosystems. Using multimodal sensors to collect data on animals' presence, activity, and existing possibilities, and leveraging various capabilities of artificial intelligence to process and interpret data for identifying needs and trade-offs, to inform design solutions that mediate different species needs, and to select solutions that maximize benefit where most needed, and to communicate relevant possibilities to different species in a species appropriate way, and to inform interfaces that enable animal dwellers to interact with their urban environment and to negotiate its challenges, and even to communicate their needs. Imagine an ecologically and ethically responsible AI that redistributes control and benefits across all city dwellers. In conclusion, we have, I would argue, a responsibility to address the existential challenges that we have created and that now face our planet, so that it can sustain all earthly life into the future. While technology could play an important role in the pursuit of a sustainable future, this will arguably depend on whether we will be able to use it to develop more harmonious relations with the beings with whom we share our common home. In this regard, I suggest that ACI's animal-centered perspective on designing technology for and with animals could not only yield design outcomes and processes that improve animals' lives and human-animal relations, but arguably and more importantly, it could produce ways of thinking and practices that are more attentive, sensitive, and empathetic towards other beings, helping us to meet the responsibility that arises from our ability to develop technology and from the power that technology gives us. This would provide us, I suggest, with an opportunity to reconfigure multi-species relations and redefine our place in the world, helping us to create more livable spaces and a more sustainable future for all. And with this, I thank you, and I'll be very happy to take questions.
All right.